So our next speaker is Ben Bloom with a last-minute talk. Ben is the CTO and founder of Atom Computing. So he will present our recent results highlight in building a scalable universal quantum computer using neural atoms. So thank you very much, Ben, for being here today. So I can see your screen and the floor is yours.
Okay, thank you. So thank you for inviting me to give this talk. I saw most of the talks didn't really go in depth about hardware, so this talk is a little different. But I think it's actually a pretty cool time to be talking about neutral atom hardware, and I'll touch on that at the very end, which is just that there's been a proliferation of results in neutral atoms very, very recently. Not just from atom computing, but from our industrial competitors as well as academic groups around the world. And so I'll tell you a little bit about all the exciting things going on there as well. So Atom Computing was a startup founded in 2018. We have one location in Berkeley, California, with one system that we're actively using right now. And we were opening a second location in Boulder, Colorado, which is a kind of a little bit of a hotbed for neutral atoms. It's where I did my PhD, and there's a lot of professors there at GILA and NIST working on this stuff. And in general, this is going to be a much larger facility with many more machines. Our goal is to develop neutral atoms into a highly scalable, externally accessible platform for quantum computing. Very specifically, we're focused on gate-based nearest neighbor couplings, or near neighbor couplings, I should say. And we're focused on just getting to qubit numbers that are actually useful for error correction. So obviously, there's lots of efforts going on to try to build a quantum computer, whether these efforts are with superconducting qubits like with IBM or Google, or with trapped ion systems like IonQ or Quantinuum. Sorry, it's a little sold. There's essentially many approaches, but they all share a set of common goals, which is high quality individual qubits, scalable qubit design and construction, and a universal gate set. So I'll talk a little bit about why neutral atoms are actually quite a good fit for this, and I'll start to show off results for how we're actually delivering on these promises. So neutral atoms, you need to get to those three common goals. In general, you want high quality individual qubits. We've updated this with some of our own results, but for a long time, trapped atom coherence times were pretty short compared to ions, and most of that is the fact that the traps themselves would affect the qubits, and I'll go into what a trap looks like and how that affects the qubit. But over the course of the last few years, people have gotten better and better at creating these traps that have incredibly long coherence times for their qubits. And they've also started showing 1Q gates being actuated over a variety of timescales, whether that's via single pulses of an ultrafast laser or whether it's via much slower, Z rotations with global X rotations. And we're also showing off a little bit of a different scheme as well. The nice thing about neutral atoms by far is, of course, the idea that you optically trap. And if you want more neutral atoms in your quantum computer, you just create more spots of light. There's obviously a lot of engineering that goes into creating more and more spots of light. But at the same time, even if you look at results from academia where the people are doing proof of principle experiments, it's very, very easy to trap, as we'll see, like hundreds of thousands of atoms. And scaling that up, both the individual control has been a kind of a little bit of an academic gold rush in the last few years for papers. So atom rearrangement has now been demonstrated over a variety of length scales, whether that's between sites over a micron or hundreds of microns. And very recently, in around mid-2010s, low atom loss imaging, where you could actually reuse the atoms and actually start talking about how you're going to do quantum error correction, as well as just speeding up data rates for actually taking the data. Very, very recently, I would say the other cool thing that's been going on is actually showing off 2-qubit gates and multi-qubit gates, whether that's having 2 atoms interact with each other, or 20 atoms, or 50 atoms. People have gotten really, really good at being able to take these systems that are intrinsically not talking to each other and have a very, very high contrast ratio for interaction on and off, and actually getting them to talk to each other now with very, very high Rabi rates on the order of megahertz or close to 10 megahertz. So how do you do this? Obviously, neutral atoms are not a very well-known platform, so I'm going to try to start from the beginning and kind of sail right through how you actually build a neutral atom quantum computer, even in these first prototype stages. So you start off with a magneto-optical trap, and this was something that was celebrated with the 1997 Nobel Prize in Physics. But in general, the idea is that you're going to laser cool atoms and use Doppler shifts to be able to take a system where atoms start out at hundreds of Kelvin of temperature and actually get them down to either millikelvin or even microkelvin temperature. So you use Doppler shifts to essentially choose to scatter photons of light off of an atom that has, a fair bit of momentum. In general, that would not have actually created a trapping environment. What the winners of the Nobel Prize realized is if you could actually create a spatially selective version of this scattering, you could actually trap the atoms, and you can create even like cool patterns and stuff like that. But you're able to actually create reservoirs now at the microkelvin temperature with millions of atoms. And this is really a great place to start. It's almost like we're building our fabrication facility for our qubits, and it's actually just a cloud that's only about a millimeter or so large, but you start off with millions of your qubits that are ready to get picked up and placed in your quantum computer. How do we do this at Atom Computing? We actually use very specific kind of strontium or just strontium in general. We start off with a hot oven. We perform this Doppler cooling via Siemens slower, and then of course we trap them in a 3D magneto-optical trap. This is the same thing that's done in many, many labs around the world. This is an image from the work I did as a grad student, where we trap these atoms to create very, very high precision clocks that are now approaching, I think, 10 to the minus 19 or 10 to the minus 20, even in fractional frequency measurement precision. So how do you go from a situation where you have millions of cold atoms that you're interested in using as qubits to actually having a single atom? Well, you can actually do this with dipole trapping. You take an objective, like a microscope objective, and you focus it down really, really tightly. And when you do that, you can overlap it with your reservoir. You can fill that dipole trap with many atoms. You can shine on some laser light, which essentially accesses almost like a photoassociation resonance, where you actually are creating molecules that get kicked out of the trap, and you're left with 1 or 0 atoms. Obviously, you probably want to create a quantum computer with more than one single qubit, so you want to actually be able to figure out a way to do this with many, many optical tweezers, if that's how you're going to code them. So you could just send many beams in the back of the objective. Obviously, we don't actually want to build a system for sending many beams in the back of an optical objective. So instead, we use these things called liquid crystal spatial light modulators, or you could use other patterning equipment to actually get the atoms into many, many traps. Once you do this, you can create very, very arbitrary trap arrays. When we did this in 2019, these are the first images we ever took of our qubits. This is actually 88 strontium. The atoms are actually kind of loaded stochastically when you do this process, and it is nice because you can kind of reload new sets of atoms. But when you start talking about how you're going to take those atoms and actually rearrange them into a useful quantum computer, you really want a tightly grouped array of atoms. Numbers start going a little faster, I apologize. One of the other cool things you could start to do that was started to be shown off in 2015 or so was you could also take those atoms and take many, many, many images of them. And this is key to being able to essentially do real-time feedback, either for quantum error correction or even just moving the atoms around. So here you have many, many different options shown in academia for how you can move the atoms around. We use an option called a kind of movable optical tweezer using acousto-optic devices. This allows us to use RF to essentially pull atoms around. When we did this, we started off building a system where you could essentially have totally arbitrary movable tweezers. We trapped atoms in them. We showed that we could create arbitrary patterns, and you could actually start dragging the atoms around and taking images of them wherever you wanted, and you could create these very, very nice patterns. What this allows us to do is, of course, rearrange the atoms into these nice, tightly fit 2D grids. And this work has also been done in 3D in Anton Brawey's group to create arbitrary 3D patterns. But we've talked a lot about how you actually create an array of atoms. How do you actually use these as qubits? Well, there's actually many, many transitions in 87 strontium. The transitions we're most interested in are these nuclear spin transitions, which are kind of very, very low frequency energy levels in the atom. But the nice thing is they couple to very, very little outside of the atom, and they're very, very insensitive to anything in the environment. The cool thing about this is you can use the laser light you're already using to cool and manipulate these atoms to both read out these atoms and also create a qubit system. So even though I had a very, very large number of low energy excitations in the atom with this I equals 9/2, I can actually do my own version of quantum engineering, not exactly depositing metal or superconducting metal and changing the properties of the Hamiltonian, but instead just adding little bits of light here and there to actually break degeneracy in the system and actually pull out a set of qubit states from this manifold of 10 states. The cool thing is, again, I can use these optical clock excitations to actually manipulate these nuclear spin and read out the qubit. And when you do that, you're left with now a qubit system you can read out with very, very low energy between these two systems. So how do you actually start manipulating the system is you actually use acousto-optics and electro-optics to define RF pulses, which allow you to rotate the qubit from one nuclear spin state to another state by creating individual spots of light that you're allowed to that you're able to control the amplitude and phase of. The cool thing about this system is that for the entire 2D array, you actually only need 8 RF channels and 1 laser to address the entire array, and this is possible to scale up to on the order of a few hundred, almost to a few thousand with just these number of channels. So it's a very, very nice scalable system for addressing these qubits. And you can create little logos and stuff like that for whoever helped you, pay for this. And in the future, we're also working with University of Washington and Sandia National Labs to help you create a more integrated photonics approach to this. So what happens when you turn on this system, say you have a system of 110 qubits and you start performing, individual rotations, you start seeing Rabi flopping, and you can start asking the questions that you wanted to ask about how with this system, which is how does it really perform as a quantum computer? How do these qubits really do? Well, first off, you can start to look into just T1. What is the T1 of this qubit? The cool thing about the nuclear spin qubit is that it just does not interact with the environment. It does not even interact with your trapping lasers, such that at the end of the day, the T1 is effectively infinite. And this is in comparison to neutral atom qubits based on alkali atoms, where there's a lot of differential coupling between the two qubit states, and you get this effective T1. Now, of course, if you're interested in these nuclear spin qubits, how they actually perform, well, you can start to perform Ramsey measurements. You can see that at 1 millisecond, they're performing the same as 1,000 milliseconds. You can start to see some decay at 3 seconds. Recent work has kind of shown that you can get this in ytterbium as well at a few second level. If you perform an echo, you can actually push this out to about 40 seconds. So each qubit now has a greater than 40 seconds coherence time. This is pretty exciting because you can start talking about feedback in a system without having to really push what is possible with classical computing. If you want to take information from the system, change what pulses you're sending and send new pulses, you have very, very little errors associated with just dealing with the classical computer. Let's skip over this for a second. The exciting thing with this is that you can start to actually now do pigsty, you can do randomized benchmarking, and you can do everything you want to do to actually turn this into a quantum computer. Similarly, I would say that in the last few weeks, the exciting thing about neutral atoms is that very recently there's just been so much work since about 2015 that there's just been a kind of huge explosion of high fidelity entangling gates. And it's a pretty exciting time because not only is the entangling gates getting better and better for neutral atoms, but the number of neutral atoms keeps going up and up and up. So even our first system is now at 100 qubits. I think the records now are at a few hundred to almost 300 qubits. And I expect we'll see systems of thousands of neutral atom qubits very, very soon, actually. So in the last few weeks, what we've seen long-lived Bell states using strontium from Adam Kaufman, many, many seconds of entangled states. We've seen the debut of 2 ytterbium platforms, both a universal gate set platform where they're showing both single qubit gates and 2 qubit gates and doing benchmarking. We've seen much faster 1 qubit gates, so essentially 150 nanoseconds 1 qubit gates for systems with coherence times in the many, many, many seconds. So it's a very exciting time to have fast gates and long coherence times. And very, very recently, we've also seen a full platform for running higher connectivity circuits, including the idea of how to do mid-circuit atom rearrangement and talking about how to do mid-circuit measurement, which is allowing them to essentially perform toric codes and surface codes and things like that. I would say the exciting thing about neutral atoms in general right now is they're entering the scene, and they're entering the scene in a very, very big way. So it's a very cool time to be working on neutral atoms. So with that, I'll say, you know, this is all work of many, many people at Atom Computing. And as always, we're hiring. So if you're interested, you should always contact us.
Thank you very much, Ben, for your excellent talk. Unfortunately, we don't have time for any question, but you can answer to the chat if someone has some question to ask to you. So thank you very much again.